Hello everyone and welcome to Signal Systems and Signal Processing with Wolfram U. This lesson will be on inverse Laplace transform. Previously, we gave the definition for the Laplace transform of the signal x of t. Inverse Laplace transform is defined as shown here. Given the Laplace transform of a function x of s, we can find x of t using this formula. LTI systems lead to transfer functions in the form of ratios of polynomials. The general form is as shown here. We will use a method called the method of partial fraction expansion to write the Laplace transform in terms of a superposition of simple terms for which the inverse transform is known. We are usually given tables of transform pairs. The terms in the expansion correspond to one of the roots of the denominator polynomial. We will go over this for two different cases, the case where we have distinct roots of the denominator polynomial and the case where we have repeated roots. In the case of n distinct poles pk, the roots of the denominator, the transform x of s may be expanded into a linear combination of first-order terms as shown here. Each constant ak is known as the residue of pole pk and is given by the expression shown here. Now, once we have this expansion using familiar transform pairs and assuming that the real part of s plus pk is positive for k going from 1 to n, we get the inverse Laplace transform of x of s as shown here. Let's look at an example. Given the Laplace transform shown here, we would like to find the signal x of t by taking the inverse Laplace transform. We use the method of partial fractions to express the Laplace transform as a summation of first-order terms. First, we find the roots of the denominator of the Laplace transform. The Laplace transform can be expanded as shown here. Since we have three roots, the order of the denominator is 3. We have 3 first-order terms. Each of the constant ak's known as the residue of pole pk can be calculated as we show here. We take the limit of s plus 1 times the Laplace transform x of s when s goes to the value of the first pole, minus 1. This is for a1. For the second constant, again, we multiply x of s by s minus the value for the second pole. And we take the limit of this expression when s goes to the second pole. We do the same for the third coefficient. Once we have these values, we can get the partial fraction form of the Laplace transform x of s as shown here. Now we are ready to find the right-sided signal corresponding to each of these terms using the known transform pairs. For example, we already know that for the right-sided exponential function shown here, the Laplace transform is 1 over s plus a when real part of s plus a is positive. So for the first part of the Laplace transform, the inverse Laplace transform would be e to the power minus t times ut. And we can do the same for each of the remaining terms. We can also find the inverse Laplace transform using the Wolfram language, and we can plot the inverse Laplace transform to see how it changes over time. We have some oscillations due to the sine and cosine, but the signal is dying over time. Now, if one of the roots of the denominator has multiplicity k, for example, the expansion takes the form shown here. And the residue an for n going from 1 to all the way to k are given using the formula shown here. We are basically multiplying the Laplace transform x of s with s plus p to the power k, and we take different ordered derivatives of that, and we have a coefficient 1 over k minus n factorial. The inverse Laplace transform of each term is obtained using the transform pairs shown here. For the two different sets of ROCs, we have the right-sided signal and the left-sided signal. Now, assuming that the real part of s is greater than negative p, the inverse Laplace transform of x of s will be the right-sided signal x of t shown here. We have k terms with e to the power minus pt. Let's look at a second example of finding the inverse Laplace transform where we have repeated roots for the denominator of the Laplace transform x of s. Again, we start by finding the roots of the denominator of the Laplace transform, and we expand the Laplace transform as shown here. We have 3 terms for the repeated root minus 2 and 1 term for the root minus 1. Then we find the residues. We're starting with the residues of the repeated root minus 2. For a1, 3, we take the limit as shown here. Second derivative of s plus 2 to the power 3 times x of s divided by 2 factorial. We find the second residue. Here we have the first derivative of the expression, and the third residue, s plus 2 to the power 3 times x of s. Finally, we find a2 for the singular root, as shown here. With these residues, we can put together the expanded version of the Laplace transform x of s. Then we can use known transform pairs to find the signal x of t itself, or using the Wolfram language, assuming that we want the right-sided signal, x of t will be as shown here. We can also plot the signal in time to see how it changes over different values of time. So for the examples that we saw so far, we assumed system causality and therefore right-sided signals, expecting that the ROC spans the right half of the complex plane. This, in fact, is the most common case encountered in practice, but let's also consider alternative ROC specifications for a given Laplace transform x of s and find the inverse transform x of t in those cases. For the Laplace transform x of s shown here, we have 2 poles p1 equal to -1 and p2 equal to -3. And this results in 3 possible ROCs as shown here. We have the half planes and the vertical strip. Let's find the inverse Laplace transform for each of these cases. For the case where ROC is given as real parts of S are greater than -1, basically the ROC spans the right half side of the complex plane. We can use the Wolfram language to find the inverse bilateral Laplace transform together with the function conditional expression to give condition on real parts of S. We can also plot to see how the right-sided signal x of t changes over time. Now to find the x of t by hand, we'll write the partial fraction expansion of x of s as shown here, and we find the values of the coefficients a and b. A, the residue of pole -1, can be found by taking the limit shown here. Similarly, we find the residue for the second pole, and using these values, we can put together the partial expansion of the Laplace transform as shown here, and use the known transform pair shown here for the first term and for the second term. Putting together these two signals, we get the value of x of t as the sum of the two terms. Now let's consider the other case of the half plane for RC, where the real part of s is less than -3. Again, using the Wolfram language, the function inverse bilateral Laplace transform together with the conditional expression to enforce the condition that the real part of s must be less than -3, we get the signal as shown here, and we can plot it to see how the left-sided signal changes over time. As expected, the signal is unbounded. When t goes to -infinity, x of t goes to infinity. Now, if we were to do this by hand, given the partial fraction expansion of the Laplace transform, we use the transform pair shown here for the left-sided signals, and we find the inverse Laplace transform for the first term and the inverse Laplace transform for the second term, and the signal x of t is given as the sum of these two terms. The final and the third case for ROC is where we have the vertical strip, when the region of convergence is where the real parts of S are between -3 and -1. Using the Wolfram language, we can find the signal x of t, and plotting the signal shows the two-sided x of t. On the right side, we have a decaying exponential that goes to 0. On the left side, when t goes to -infinity, the signal is unbounded. And again, finding the inverse Laplace transform by hand, given the expansion of the Laplace transform, we use the transform pair with the left-sided signal for the first part of the Laplace transform and the other transform pair for the second part of x of s. Adding these two expressions, we get x of t. So in this lesson, we gave the definition for inverse Laplace transform, and we found the inverse Laplace transform of rational functions using the method of partial fraction expansion. We looked at several examples of finding the inverse Laplace transform, and we looked at this assuming different regions of convergence.